Hey class, Adam Ward here. Let's talk today about fluid mechanics, and in particular I want to talk with you today about pressure variation as we move in the horizontal and vertical directions within a fluid. So as a reminder to you, this lecture is still about the fluid statics portion of class, so we're thinking about fluids that are not moving, so velocities of zero at this point. So to motivate ourselves, we're going to start out by picturing a cube of fluid. If it helps you, picture that we went up to the rec center and we've picked out some 1 meter by 1 meter by 1 meter cube of water that we want to analyze. And our goal is to see how does pressure change as we move horizontally or vertically within that cube. So I've given our cube dimensions of x, y, and z. And the fluid statics problem means that nothing is moving in our system. And in order for that to be the case, the sum of the forces has to equal zero in all three dimensions. So in the x and the y and the z, meaning there is no net force. That doesn't mean there are no forces, but it means they have to be perfectly opposing one another. If we had one force that was larger than the other, the result would be motion. That would cause the system to move. So we know that those forces have to equal zero. And the x and y dimensions are what we're going to think about here. I'll do this derivation for the x, but you could repeat it yourself for the y if you wanted. It's identical. So we're going to focus on horizontal first. And the other thing that we're going to need to invoke here is the idea that in the middle of our cube there is some pressure, which we're going to call PC for center. And to sort of prime you for where some of this is going to go, we'll need to know something about the area of the different faces of our cube. And so for example, the area that I've highlighted in green, the area of that could be calculated as the y dimension multiplied by the z dimension. So delta y times delta z in this case. Okay, so there's our little cube on the right hand side. And in the horizontal direction, we know that the sum of forces must be zero. And if we could picture separating that cube out, or trying to set a plexiglass cube in there and asking what would be pushing on our plexiglass cube in that direction, we might have pressure due to the fluid on the left and pressure due to the fluid on the right. Now, if you're watching this and saying to yourself, yeah, what about the weight? What about the bottom? What about the top? Those are in other dimensions. Those forces are actually acting in the z dimension that I just described, and we'll do those next when we look at vertical. So along that x-axis, we've just got these two forces. And I'll use these colors purple and blue throughout to try to help keep us organized. So one of the things that we could remember is the definition of pressure tells us that a pressure is a force per unit area. So we could describe these forces based on the pressure on each face multiplied by the area. So I'll go ahead and make those substitutions here. Now, you'll notice that I've switched in a minus sign for the force on the right. And so what I've done is define that moving to the right would be the positive direction for us, and moving to the left would be the negative direction. So these forces have directionality to them, and I'm taking care of that with the minus sign. And we're going to update two things in this equation. First is the areas. As we noted on the previous page, both the area of the left and the area of the right are equal to delta y times delta z. That was the face of the cube highlighted in green on the previous slide. Now the second thing we need to do is deal with those pressures, like the pressure on the left and the pressure on the right. So we may not know what those pressures are, but we do know that we did define this pressure at the center of the cube, right? And regardless of what those pressures are, we ought to be able to describe them based on the known pressure in the center, PC, and then the distance, so delta x over 2, multiplied by the rate of change, or the slope of that pressure through the cube. So where did those come from? Delta x over 2 is a distance, and then that dp dx, that's the rate of change of pressure as you move in the x direction. We don't know what it is, but the idea here is that if we worked in an infinitesimally small volume where that delta x became incremental, that we could linearize this equation at this location. So we'll define our pressure on the left using that terms written in purple. And in parallel, we'll do the same for our pressure on the right. So we don't know what those values are, but we can now describe them based on the pressure in the center, distances, and some gradient in pressure across the cube. So when we plug those in to our working equation here, we get, again, all the purple, we get the force on the left-hand side of the cube, and all the blue, the forces on the right-hand side of the cube. We can start to cancel out some terms and combine some terms, and we end up with delta x times delta y times delta z, so the three dimensions of the cube multiplied by that pressure gradient has to equal 0. Now, the dimensions of the cube can't be 0. Those are physical quantities. They describe an actual length scale in all three dimensions. So if those can't be 0, the only solution to this problem is that dp dx must equal 0, or the horizontal gradient in pressure is equal to 0. So put another way, there is no pressure variation as we move horizontally through a fluid. Right? We can move along that x dimension, and we can know that the pressure at any two locations, moving only along that axis, will be identical to one another. Now the next slides we're going to do the same sort of derivation, but we'll describe how pressure varies as we move in the vertical or z dimension. So again, we've got our cube with its dimensions and the pressure at the center of the cube. Now, working in the z dimension, we're going to have three forces to keep track of here. So in purple, I've drawn a pressure force pushing down on the top of the cube, and notice I've assigned that a negative sign because it's pushing down, which means I'm assuming that z is positive in the upward direction here. And I'll go ahead and label that on our drawing, just to remind myself of the convention I've established. Force pushing up on the bottom in blue, and then in the vertical we've also got weight. So this block of fluid itself is being pulled toward the earth by gravitational forces, and so there's this additional force pulling down in the vertical dimension. The top and bottom will use the exact same approach as we did in the horizontal, approximating that gradient across the cube from top to bottom. So the new thing here is adding this weight force. And of course, how much does something weigh? Well, it's the volume multiplied by the specific weight. And the volume of our cube is delta x times delta y times delta z. And there's a gamma for specific weight. So we're going to proceed by now substituting in these definitions the same as we did for the horizontal for top and bottom, and then this definition for weight. So here we go. Sum of the forces in the z direction has to be 0. And you can see in purple, I've gone ahead and written in the force pushing down from the top. And just a reminder, that was the pressure we think exists at the top multiplied by the area of the top. We can do the same for that upward force pushing on the bottom and the weight force. So using those colors to try to help keep track of where these terms came from. So we can do a little bit of algebra, and we can simplify this equation down. And what we find out is that dp dz in this case has to equal the negative specific weight. Now, just as a reminder to you, that's a specific weight, which you could also write as a density rho multiplied by a gravity g. And so if you change the acceleration, you actually can change the way that this pressure gradient works. What's an example of that? When you are in an elevator and it accelerates upward, that means that the things in the elevator are being pulled up faster than gravity is pulling them down. So if you accelerate upward, for example, or accelerate downward in a fall, that gravitational term might affect things. Finally, we're going to get this into maybe a more useful form. So starting from the equation we had on the previous slide, I'm going to separate the variables, and I'm going to integrate both of those. And so when we do that, we get pressure on the left is equal to minus specific weight times z plus a constant. And that constant, you'll recall, that arises from a constant of integration when we go through that problem. So we can do some manipulation of this algebraically, and what we can find is that pressure divided by specific weight, so P over gamma, plus our elevation, Z, is constant as we move vertically through a fluid. Right, so if we're moving down or up, what we're doing is trading elevation for increased pressure when we move down. This is handy to us because we can actually then relate 2 points within a fluid using this equation. P1 over gamma plus Z1 equals P2 over gamma plus Z2. So at the end of this derivation, there's 2 critical things that you should know. One is that you have mathematically proven to yourself that as you move in the horizontal, pressure does not change. As you move in the vertical, pressure does change, and you have the ability to relate 2 points to one another depending on their pressures and their elevations. This is an equation that we're going to use for a couple of lectures. I may call this our fluid statics equation. So you need to know how to use this and apply it. I will not ask you about the derivation in any way, shape, or form, but I wanted you to see where it comes from and how we can prove to ourselves some of these basic properties and principles that we'll use this semester. All right, thanks everybody, and I'll see you in class.